When dealing with electrical installations involving multiple loads supplied from a single overcurrent protection device, adhering to the National Electrical Code, or NEC, is crucial for safety and compliance. In the context of feeding two rooftop units, or RTUs, from an existing 400 amp breaker using a 3-inch electrical metallic tubing, or IMT, conduit, the question of conductor sizing arises. The NEC provides specific guidelines to ensure that the conductors are adequately sized to handle the intended load and potential overcurrent conditions. NEC Section 440.22b addresses the sizing of conductors supplying more than one hermetic refrigerant motor compressor. This section stipulates that the conductors supplying two or more hermetic refrigerant motor compressors must have an ampacity equal to at least the sum of the rated load currents or branch circuit selection currents, whichever is greater, of all the compressors plus 25% of the current of the largest motor compressor in the group. NEC Section 430.24 pertains to the sizing of conductors supplying several motors. It states that conductors supplying two or more motors must have an ampacity equal to the sum of the full load currents of all the motors plus 25% of the highest rated motor in the group. The interpretation and application of these NEC sections are paramount in determining the appropriate conductor size for the specific scenario presented. With two RTU, each having a minimum circuit ampacity, or MACA, of 122 amps and a maximum overcurrent protection, or MOC, of 150 amps, and utilizing an existing 400 amp breaker, the NEC mandates that the conductors must be sized for the full rating of the overcurrent protection device. The rationale behind this requirement is to ensure that the conductors can safely handle the potential fault current that the 400 amp breaker is designed to interrupt. Reducing the conductor size based on the combined MCA of the RTU would create a situation where the conductors could be undersized relative to the overcurrent protection device, potentially leading to overheating and fire hazards in the event of a fault. The NEC prioritizes safety by requiring the conductors to be sized to match the overcurrent protection, providing a robust safety margin against overloads and short circuits. The practical implication of this requirement is that the existing conductors within the 3-inch ENT conduit must have an ampacity of at least 400 amps. This means that the conductors must be of a size and type that are rated to carry 400 amps continuously under the prevailing insulation conditions, taking into account factors such as ambient temperature, conduit fill, and conductor insulation type. The NEC provides ampacity tables, such as those found in NEC Table 310.16, that list the allowable ampacities of various conductor sizes and insulation types under different conditions. These tables must be consulted to select the appropriate conductors that meet the 400 amp requirement. It is important to note that the ampacity of a conductor can be affected by factors such as the number of current-carrying conductors in a raceway or cable, the ambient temperature around the conductors, and the type of insulation used on the conductors. The NEC provides adjustment and correction factors to account for these factors, ensuring that the conductors are adequately sized for the specific installation conditions. In the scenario of splitting the conductors at two fuse disconnects next to each other, the same conductor sizing principles apply. The conductors from the 400 amp breaker to the fuse disconnects must be sized for 400 amps, and the conductors from the fuse disconnects to each RTU must be sized according to the MCA and MOP requirements for each RTU. Each fuse disconnect should have an overcurrent protection device, such as a fuse, that is sized appropriately for the RTU it is serving, not exceeding the MOP rating of the RTU. In summary, NEC 440.22b and 430.24 require that the conductors feeding the two RTU from the existing 400 amp breaker must be sized for the full 400 amp rating of the breaker. This ensures that the conductors are adequately protected against overloads and short circuits, maintaining the safety and integrity of the electrical system. Ignoring these code requirements can result in dangerous situations, including overheating of conductors, insulation breakdown, and potential electrical fires. It is always recommended to consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and standards when performing electrical work. Let's delve deeper into the NEC articles mentioned and explore their implications. NEC Article 440 addresses air conditioning and refrigeration equipment. Section 440.22 specifically covers the sizing of branch circuit conductors for equipment with a hermetic refrigerant motor compressor. Subsection B focuses on installations with 2 or more compressors. The key takeaway is that the conductors must be sized to handle the combined load of all compressors, with an additional allowance for the largest compressor. NEC Article 430 deals with motors, motor circuits, and controllers. Section 430.24 outlines the requirements for sizing conductors supplying 2 or more motors. Similar to Article 440, this section mandates that the conductors must have an ampacity sufficient to carry the sum of the full load currents of all motors plus a percentage of the highest rated motor. The overlap between these two articles is significant because rooftop units often incorporate both motor-driven compressors and other motor loads, such as fans. Therefore, it's essential to consider both articles when determining the appropriate conductor size. Now, let's address the practical implications of using a 400 amp breaker for 2 RTU with MCA of 122 amps each and MOPs of 150 amps. While the combined MCA of the 2 RTU is 244 amps, which is significantly less than 400 amps, the NEC requires the conductors to be sized based on the overcurrent protection device, not the load. This might seem counterintuitive, but the rationale is to protect the conductors from potential fault currents. If a fault occurs, such as a short circuit, the 400 amp breaker is designed to trip and interrupt the current flow. However, if the conductors are sized for only 244 amps, they may not be able to withstand a high fault current for the duration it takes the breaker to trip, potentially leading to overheating and insulation damage. Therefore, the conductors must be robust enough to handle the full 400 amps until the breaker clears the fault. To comply with the NEC, the existing conductors within the 3-inch GNT conduit must be replaced with conductors that have an ampacity of at least 400 amps. The specific conductor size will depend on the conductor material, insulation type, and installation conditions. For example, using copper conductors with a 75 degrees Celsius insulation rating such as THW-N-2 or XHHW-2 would typically require a minimum size of 600 kcmil to achieve an ampacity of 400 amps. However, if aluminum conductors are used, a larger size would be necessary to achieve the same ampacity. It's crucial to consult NEC Table 310.16 and any applicable adjustment or correction factors to determine the appropriate conductor size for the specific installation. In addition to the conductor size, the overcurrent protection devices at the fuse disconnects must also be properly sized. These devices should be sized according to the MOP rating of each RTU, which is 150 amps in this case. The purpose of these disconnects is to provide local protection for each RTU and to allow for safe isolation of the equipment for maintenance or repair. The fuses or circuit breakers at the disconnect should be selected to coordinate with the 400 amp breaker, ensuring that the disconnects trip before the main breaker in the event of a fault within the RTU. This coordination helps to minimize the impact of a fault and to prevent unnecessary shutdowns of both RTU. When splitting the conductors at the fuse disconnects, the conductors from the 400 amp breaker to the disconnects must still be sized for 400 amps, as they are still part of the main feeder circuit. The conductors from the disconnects to each RTU can be sized according to the MCA and MOP requirements for each RTU, as they are now considered branch circuit conductors. However, it's important to ensure that the conductors are properly protected at the point where they are tapped from the main feeder circuit. This can be achieved by using properly sized fuses or circuit breakers at the disconnect. In summary, when installing 2 RTU with MCA of 122 amps each and MOPs of 150 amps on an existing 400 amp breaker, the conductors from the breaker to the fuse disconnects must be sized for 400 amps, and the conductors from the disconnects to each RTU must be sized according to the MCA and MOP requirements for each RTU. The overcurrent protection devices at the fuse disconnect should be sized to coordinate with the 400 amp breaker and to provide local protection for each RTU. Adhering to these NEC requirements will ensure a safe and reliable electrical installation that protects against overloads and short circuits. Always consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and standards. Furthermore, consider the directing factors that may apply to the conductors in the 3-inch ENT conduit. The NEC specifies directing factors for situations where multiple current-carrying conductors are installed in the same conduit. The directing factors are based on the number of current-carrying conductors and the ambient temperature. If the conductors are installed in a high ambient temperature environment, the ampacity of the conductors must be reduced to account for the increased heat. The NEC provides tables that list the directing factors for different numbers of conductors and ambient temperatures. It's essential to apply these directing factors correctly to ensure that the conductors are not overloaded. In addition to the directing factors, the voltage drop in the conductors must also be considered. Voltage drop is the reduction in voltage that occurs along a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop in branch circuits and feeders to a maximum of 3% and 5% respectively. To minimize voltage drop, it's important to use conductors that are large enough to carry the load without excessive voltage drop. The voltage drop can be calculated using Ohm's law and the conductor's resistance per unit length. The NEC provides tables that list the resistance per unit length for various conductor sizes and materials. It's crucial to perform voltage drop calculations to ensure that the voltage at the RTU is within acceptable limits. Another important consideration is the grounding and bonding of the electrical system. Grounding is the process of connecting the electrical system to the earth, which provides a low impedance path for fault currents to return to the source. Bonding is the process of connecting all metal parts of the electrical system together, which creates an equipotential plane and reduces the risk of electric shock. The NEC specifies detailed requirements for grounding and bonding, including the size and type of grounding and bonding conductors, and the methods for connecting them. Proper grounding and bonding are essential for ensuring the safety of the electrical system and for protecting against electric shock hazards. Finally, it's important to document the electrical installation thoroughly. This includes creating accurate wiring diagrams, labeling all equipment and conductors, and recording all relevant information about the installation, such as conductor sizes, overcurrent protection device ratings, and grounding and bonding connections. Proper documentation is essential for future maintenance, troubleshooting, and modifications to the electrical system. It also helps to ensure compliance with the NEC and other applicable codes and standards. In conclusion, installing 2 RTU on an existing 400 amp breaker requires careful consideration of the NEC requirements for conductor sizing, overcurrent protection, directing, voltage drop, grounding, bonding, and documentation. Adhering to these requirements will ensure a safe, reliable, and code-compliant electrical installation. Always consult with a qualified electrician or electrical engineer to ensure that all applicable codes and standards are met. Remember to check local codes in Tennessee to ensure compliance with all state and local regulations. These may be more stringent than the national code. The NEC is updated every 3 years, so ensure you are using the latest edition adopted by the local jurisdiction. Let's also talk about the importance of proper coordination between the overcurrent protection devices. Selective coordination is a design approach that ensures that only the overcurrent device closest to a fault will open, minimizing disruption to the rest of the electrical system. In the case of the 2 RTU, the fuses or circuit breakers at the fuse disconnect should be sized and selected to trip before the 400 amp breaker in the event of a fault within one of the RTU. This can be achieved by using fuses or circuit breakers with different time current characteristics. Time current curves illustrate the relationship between the magnitude of the current and the time it takes for an overcurrent device to trip. By comparing the time current curves of the fuses or circuit breakers at the disconnects and the 400 amp breaker, it's possible to determine whether selective coordination will be achieved. If the curves intersect, it means that both devices could potentially trip simultaneously, which is undesirable. Selective coordination is not always required by the NEC, but it's the best practice that can improve the reliability and safety of the electrical system. Another important aspect of electrical installations is arc flash hazard analysis. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault creates an arc of electricity. The arc can generate intense heat and pressure, which can cause severe burns, injuries, and even death. An arc flash hazard analysis is a study that identifies the potential arc flash hazards in an electrical system and determines the appropriate safety measures to mitigate those hazards. The analysis typically involves calculating the incident energy, which is the amount of energy that a worker would be exposed to in the event of an arc flash. Based on the incident energy, appropriate personal protective equipment, or PPE, can be selected. PPE can include items such as arc-rated clothing, gloves, face shields, and helmets. The NEC requires arc flash hazard analysis to be performed for certain electrical equipment such as switchboards, panel boards, and motor control centers. However, it's a good practice to perform an arc flash hazard analysis for all electrical equipment, especially in industrial and commercial settings. In addition to PPE, other safety measures can be implemented to reduce the risk of arc flash. These measures can include installing remote racking systems, using current-limiting fuses, and implementing lockout-tagout procedures. Lockout-tagout is a safety procedure that ensures that electrical equipment is energized and isolated before work is performed on it. By implementing these safety measures, it's possible to significantly reduce the risk of arc flash injuries. Let's also consider the impact of harmonic currents on the electrical system. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the electrical system, which is typically 60 Hz in the United States. Harmonic currents can be generated by nonlinear loads, such as electronic ballasts, variable frequency drives, and computers. Harmonic currents can cause a variety of problems in electrical systems, including overheating of transformers and conductors, increased voltage distortion, and malfunction of sensitive electronic equipment. To mitigate the effects of harmonic currents, it's important to use harmonic mitigation techniques, such as installing harmonic filters or using harmonic mitigating transformers. Harmonic filters are devices that block or reduce the flow of harmonic currents. Harmonic mitigating transformers are transformers that are designed to reduce the generation of harmonic currents. By implementing these techniques, it's possible to improve the power quality and reliability of the electrical system. Finally, let's discuss the importance of ongoing maintenance and testing of the electrical system. Electrical equipment should be inspected and tested regularly to ensure that it is operating safely and reliably. This can include visual inspections, insulation resistance testing, and circuit breaker testing. Visual inspections can identify potential problems such as loose connections, damaged insulation, and corrosion. Insulation resistance testing can detect insulation breakdown, which can lead to electrical faults. Circuit breaker testing can verify that the circuit breakers are tripping properly and are providing adequate protection. By performing regular maintenance and testing, it's possible to identify and correct potential problems before they cause failures or safety hazards. This can help to extend the life of the electrical equipment and to improve the overall reliability and safety of the electrical system. In summary, installing 2 RTU on an existing 400 amp breaker requires a comprehensive understanding of the NEC requirements for conductor sizing, overcurrent protection, dirty voltage drop, grounding, bonding, coordination, arc flash hazard analysis, harmonic mitigation, and ongoing maintenance and testing. Adhering to these requirements will ensure a safe, reliable, and code-compliant electrical installation. Always consult with a qualified electrician or electrical engineer to ensure that all applicable codes and standards are met.